Our mission is to deliver urgently needed supplies using an unmanned ground vehicle. The terrain is semi-barren with dirt roads, obstacles, and open terrain. Hills in the area impede radio transmission, so we cannot directly teleoperate the vehicle. It must rely on its onboard resources, sensors, processing, and maps to drive safely to its goal. The vehicle is a converted Army ambulance Humvee called the Navlab 2. It has been retrofitted with electric actuators to turn the steering wheel and to control the brake and throttle. The vehicle has been outfitted with generators, computer workstations, and an experimental high-speed processor. The Navlab 2 has a video camera mounted inside, a scanning laser rangefinder on the roof, and an accurate gyro compass. The testbed vehicle also contains air conditioning, seats, and displays for onboard researchers. Researchers at Carnegie Mellon University have developed an array of techniques for autonomous driving. Alvin is a simulated neural net program that learns how to drive by watching the video images and steering wheel positions as a person drives. After about 5 minutes of observation, it has learned to associate input images and steering outputs and can drive the vehicle. Alvin has learned to drive on a variety of roads and has run as fast as 55 miles per hour and as far as 22 miles. YARF is a model-based road-following program with specialized routines for tracking lines, stripes, and other features. It fits tracked features to its model of the road, then interprets observed and missing features in terms of lighting changes, occlusions, changes in lane structure, and other scene events. It is designed to detect approaching intersections, find the correct lane for turning, and make the turn. Images from the scanning laser rangefinder are interpreted in several different modes. For quick obstacle detection, the range data is first converted to elevation data and stored in a grid map. The data within each grid cell is used to fit a plane. If the planes in several neighboring cells are too steep, that area is declared to be an obstacle. In rougher terrain, it is not adequate to just extract symbolic obstacles. Instead, the desired trajectory is tested by simulating vehicle traversal over the elevation map built from the range data. At each step, the vehicle is placed on the terrain and is tested to see if it would tip over, become hung up or entrapped, go over too big a step, or bounce into the air. This analysis can rule out a path or can allow a path but limit the maximum speed. This method has been used to drive cross-country for an hour and a half continuously. Vehicle speed is currently limited to 5 miles per hour due to the limited range, resolution, and sensing speed of our current laser scanner. Further laser processing is used for recognizing objects, such as landmarks. In open terrain, it is sufficient to note the 3D size and location of a cluster of range points. For more complex scenes, surface models of each object must be extracted from range images and tracked between images. The operator planning today's delivery mission begins by consulting a map. This particular map was built by the vehicle itself on previous runs. It contains locations and descriptions of roads, general locations of areas cluttered with obstacles, and landmark locations and descriptions. The operator interactively plans the mission using a menu-oriented interface to indicate where to drive and what modules to use. The first segment of the mission follows a road known to be clear of obstacles. The planner selected Alvin to drive this stretch. 15 times a second, Alvin digitizes an image, does some simple pre-processing, then feeds the data to its simulated network. The network directly outputs a steering command. The vehicle drives this stretch of the road at up to 15 miles per hour. While driving, the map system is continually updating vehicle position. The navigator keeps track of approximate distance and direction traveled by dead reckoning, based on the gyro compass and encoders on the drive shaft. Position errors gradually accrue due to wheel slip. These errors are filtered out by matching road position on the map with perceived road location and by detecting and recognizing landmarks. When the vehicle enters the next segment of its mission, the map system automatically sends messages to perception and planning modules. In this area, the operator knew there were obstacles on the road. The mission plan stored in the map tells the vehicle to keep running Alvin to see the road, but to slow to a speed where it can safely see and avoid obstacles. At each instant, the obstacle avoidance and road following perception systems each look at a set of arcs that the vehicle could drive. The arc which gets the best combined score from the perception modules is selected to steer. Coming into the open area, the map again cues the vehicle to change modes. It turns off Alvin and starts following a designated path off the road while avoiding obstacles. Eventually, the Navlab 2 detects a landmark in its map, positions itself at its goal location, and comes to a stop. The supplies arrive in time.